Welcome everyone. Thank you for joining us for episode 19 in the Gleeble webinar series. My name is Dan Quigley. I'm the Director of Business Development and Marketing here at DSI, but more importantly, I'm your host for today's webinar. I'd like to thank Dr. Brian Allen for hosting last week while I was out of the office. Today's presentation features the Lumet measurement system, and we're really excited about the Lumet because it's so powerful and has helped drive really impressive results, in particular accelerating the development of new alloys and processes. One of the things you'll hear about is the ability to replace days or weeks of studies that may yield only a few measurements on quenched samples with a single in-situ laser-ultrasonic test that yields hundreds of measurements. And if you've heard us talk about new Gleeble developments over the past few years, you've probably heard us talk about the Lumet, but today we're bringing in one of the experts that really helped develop and optimize the system, Dr. Thomas Darson. But before I hand over the microphone, I want to make a couple of points. As always, our goal will be to keep this webinar to 1 hour or less. If you have questions during the presentation, please submit them using the chat feature here in the webinar. Our team will be available to answer some questions directly via the chat. And if time allows, we'll have live Q&A following the presentation. Video of this presentation will be available online soon, and certificates will be emailed to you if you are listening to this live. You'll be able to find a link to this video as well as videos of past webinars by going to our website at gleeble.com and clicking on the resources link in the top navigation bar. Then click on webinars. And once you're on that page, you can view past webinars and sign up for future webinars. And I'm excited to announce that next week's webinar will feature Dr. Vinod Kumar from Steel Authority of India Limited, or SAIL. Dr. Kumar is a leader in the Indian metallurgical community and a wonderful resource to the Indian steel industry. We're honored to have him present some of his experiences using the Gleeble to drive innovations in steel product development, process optimization, yield improvement, and failure analysis. Again, you can sign up for next week's webinar on our website. But today, it's my pleasure to introduce our presenter, Dr. Thomas Darson, who I first met about 10 years ago when he was a researcher at the University of British Columbia. He and the team there were doing very innovative work with laser ultrasonics and the Gleeble. He's since taken a position with Technar in Montreal in the physics and metallurgy group. And Technar is a partner of BSI and produces much of the Lumet equipment. And they also provide expertise and support for researchers and production engineers around the world. So it's my honor to welcome Thomas. So Thomas, thank you for preparing this presentation, and I'll hand over the microphone to you.
Thank you, Dan. Thank you very much, all the team at Gleeble, which have invited me for this webinar. And good morning, good afternoon, everybody, which have shown interest on participating to this webinar. I have here compiled sets of work which we have done in UBC for the last 10 years, and I'm very glad to introduce to you this sensor, which I'm sure has a very bright future ahead of us. So I'm gonna head straight into the point on real-time in-situ sensing of microstructure evolution. So here, this sensor is really dedicated for acquiring microstructure property in real time during Gleeble simulation. I have to thank many of the students which have contributed to those studies, as well as the professors, which have been a great companion over the years. So, as Dan has introduced, Lumet, or laser-ultrasonic for metallurgy sensor, is a complementary tool for metallurgical processes. And of course, we know that most of the large structures, could be bridges or cores, are produced from large steel products which are submitted to complex thermomechanical processes. And during those processes, a number of metallurgical process occurs, and they need to be controlled using different type of sensor. We know in Gleeble there is a series of sensors. We can measure stresses, strain, we can measure dilation of samples, and thanks to Lumet, we have access to additional parameter which I will describe today. So before we begin on talking more about the properties of the microstructure, I'd like just to show you what it looks like. This Lumet sensor looks like an attachment to the Gleeble machine. You can see the different part in green. It consists of two cabinets which contain the optics and the electronics. and a probe which contain the lasers. So lasers are going to be firing on the sample located inside the Gleeble chamber, and those lasers are going to generate ultrasound inside the microstructure. Those ultrasound will be having properties that will be function of the microstructure property. I have shown you here two different pictures to illustrate that this sensor can work as well on cylinder sample or plate sample that you are used to use in the Gleeble machine. So here is a little video in which I have recorded a heat treatment of a flat sample, which has been submitted to a welding cycle. So it's a very rapid heating and a very rapid cooling. What you could see here, a bright spot in the center of the specimen, is the laser firing periodically on the sample. So here is a detailed view, a schematics view of the different processes occurring during the measurement. There is two different lasers, one generation laser which generates the pulse inside the microstructure, and a detection laser here in the infrared domain, which looks at these ultrasound pulses arriving back in the surface of the sample. This system features the capabilities to acquire up to 50 waveforms per second. So those waveforms can be visualized here, and those peaks that you see on the waveform corresponds to the moment in which the pulse comes back at the generated surface. So you can see that we can measure many times the pulse coming back at the generation surface. Another important feature of this sensor is that it generates an ultrasound pulse which contains a broad range of frequency. Typically, we can access frequency ranging from 1 to about 40 megahertz. Of course, as we will see, depending on the microstructure properties, those high frequency tends to be attenuated quite a lot. So the broadband, the effective broadband that we can use can tend to be a little smaller. To ease the analysis of those ultrasound for metallurgists, we've developed a software that will be dedicated to the analysis of the properties of those ultrasound in order to provide to the metallurgist directly microstructure properties such as grain size or fraction recrystallize or fraction transform during a phase transformation, as you will see. This is important to use this type of software because it will be analyzing a number of features that corresponds to signal to noise, which is an important factor in terms of ultrasound. It will analyze the maximum frequency that can be resolved, and all this is done automatically by the software, making it very easy to use for a new user of this sensor. So let's look a little bit deeply into the waveform itself. This is the signal that we measure using the Lumet system. This signal consists of several echoes, as I've said before, and mainly two parameters are extracted to this, from this waveform. The first parameter is called the velocity, so it's the speed of sound, and it can be deduced by doing the ratio between the propagation distance, which is often twice the thickness of the sample, divided by the delay, and the delay is simply the time between two successive echoes. Another parameter that can be interested to evaluate is the attenuation. The attenuation corresponds to the decay between one echo and the subsequent echo. It can be evaluated in different manner, and often we look at this attenuation as alpha, which is a function of the frequency. So we know that this attenuation will be different at every frequency of these ultrasonic pulses. We divide by the propagation distance so as to have an attenuation per unit length, so as to be independent on the thickness of the sample. So a microstructure in metals is composed of grain. We all know that. Those grains have a crystallographic structure, and often in metals, those crystallographic crystals are oriented in different direction. This is what I have represented here in this map, in which the color corresponds to the speed of sound for a wave which propagates vertically in the sample. So you can see that there is a broad range of speed of sound for each grains. I have shown here a distribution of velocity for a sample. And you can see that depending on the texture of the sample, there will be a different distribution of this velocity in the sample. Why is it so important? It's so important because if this distribution changes because of phase transformation, because of recrystallization, therefore we will see a change in the speed of sound. So therefore I have shown here a general expression for the speed of sound in metal, which is the sum of the elastic properties of grains divided by the density of the metal. So now the second parameter, what are the sources of the attenuation in metals? So this is a little bit more tricky. There is several sources of attenuation, and we generally summarize those sources in three separate parts. The first one is the internal friction, A, which is generally considered as weakly frequency dependent, so almost non-frequency dependent, at least in the range that we can acquire. And it's often due to the presence of little defect in the sample, such as dislocation or moving of carbon atom between lattices, and this contribution is usually small. The main contribution that we are very interested in is the grain scattering contribution. We will come back to this contribution, but this scattering occurs because the grains are oriented in different directions and the wave will be scattered in various directions due to those grains present in the sample. And the third contribution can be summarized as due to the geometry of the specimen and is simply representing the dispersion of the wave, the diffraction of the wave inside the sample as it propagates through the sample. So you see here, if we were to measure the attenuation using 2 echo, that is to say the ratio between the amplitude of this echo by this echo, these 2 echo have 2 different propagation distance. So therefore, this one has propagated twice more than this one. And so we can consider that this diffraction contribution in this method will be different for this echo and this echo. Therefore, it's hard to measure attenuation in this method because we cannot extract only the grain scattering contribution. About 10 to 15 years ago now, maybe even 20 years ago, the new method's been applied by the Canadian CNRC, where the method is to use one single echo, which have therefore been propagated the same propagation distance, and which isolate this contribution from grain scattering. So what we have to do is measure a waveform in a reference sample, and therefore, while we will be measuring the current waveform by doing the ratio of those 2 echoes, we will have only the contribution from the grain scattering in the attenuation. We can then write the attenuation as being a function of the frequency and the grain size as such to build some calibration and determine grain size from this measurement of the attenuation. So if we look into literature, we will see that the attenuation due to scattering by grains is usually written as grain size to the power of an exponent times the wavelength to the power of an exponent. Wavelength is simply the inverse of the frequency. So you see here is depending on the frequency and the grain size, you will have different relationship between the attenuation and the frequency. And so we usually talk about regime of scattering. In metals, we are interested of mainly 2 regimes, the Rayleigh region and the stochastic region. And mostly, to simplify things, we can assume that we are usually into one single regime, and construct those calibration this way. So if we were to just try to validate those theory from simulation, we can build some microstructure using finite element microstructure. We can create some microstructure, attribute some properties of each grain, those elastic property, which reminding ourselves they are anisotropic in metals. And we can then build some attenuation spectrum that we can see here. So I have seen here in comparison the attenuation spectrum that we can measure from the finite element analysis, some attenuation spectrum that we can measure in Lumet, and then you can see here that there is a good correspondence between those two. So here we can reassure ourselves that those theories here in dashed line are actually in very good agreement with the measurement that we can do in Lumet. We can validate as well some complex microstructure using some simulation tools. So I'd like to point out this very first calibration, which has been done by the CNRC about in 2005, which was a breakthrough in metallurgy because it would allow the measurement of the austenite grain size in real time. So as we know, austenite is only a phase which is stable at high temperature, and so it's often a challenge for metallurgists to control this austenitization treatment because they don't know the grain size that they have in their furnaces. So therefore, using this machine, we can access in real time the grain size in austenite for various conditions. Since then, a number of other calibration has been constructed in other metals, but this simple relationship between attenuation and B, which is a function of grain size, is usually well established. So I just want to show you here what happened in other metals. Like I said, we have developed calibration for austenite, which is the iron FCC here. And I want to show that this type of relationship applies to other metals like titanium, copper, aluminum, and niobium, among others. Here is a nickel-based superalloy. What I want to show here in this slide is that it's not easy to measure grain size in all material the same way. The reason is that the attenuation will not be as intense in some material which are weakly anisotropic, such as aluminum. So it's usually very difficult to access a measurement of grain size in aluminum when it is very easy to measure grain size in nickel, in austenite, like I said, and in titanium BCC, for instance. So now that I've talked a little bit about these theories of ultrasound and how we can access microstructure properties, I'd like to go straight to case studies, which is the best way to illustrate the capacity of this machine. The first case studies that I have chosen illustrate the measurement of grain size in steel. And so here for this steel, we've chosen a plain carbon steel, A36, which composition is indicated here. And in this alloy, what's important to notice is that there is aluminum nitride precipitate, which tend to dissolve around the temperature of 1100 degrees. This dissolution of precipitate, which occurs simultaneously to the austenite grain size, will have an impact on the way the grain growth will occur, as we will see. So the test schedule is indicated here. It's a typical heat treatment for austenitization, go high temperature, stay for a little bit, and then going down. This is the initial microstructure, and this is a typical sample used for the Lumet testing. Okay, so these are the results that we can see here. In the vertical axis are the austenite grain size, varying from 0 to about 150 degrees, depending on the condition. And here, depending on the temperature, of course, you will have different limiting grain size. At 950, we can see almost no grain growth. Around 1050 degrees, we have a limiting grain about 100 micron, and at 1100 degrees, the grains are slightly larger, about 120 micron. what was quite interesting in this alloy is at 1000 degrees, you see, we have done many tests, and every time that we would do a test, the grain growth curve will always be very different. You can see that the sharp rise in grain size occurs either very shortly after the onset of isothermal holding, or only about 100 to 150 seconds after the onset of isothermal holding. So this is typical sign of abnormal grain growth occurring inside the sample. I will show you here what we can see in the microstructure after quenching the sample. These are tests that we can do. If we quench the sample, we can visualize the microstructure and observe that there is patches of martensite here in the sample, and those martensite are a sign that the grain size of austenite in this zone were much larger than the grain size in those zones here where we have more like a benite matrix. The reason why it's martensite is as the grain size of austenite is increased, the austenite decomposition will occur at much lower temperature, forming therefore martensite instead of benite. And what you can see here is that depending on where we would measure the austenite grain size, then we may not have the same average grain size in the bulk of the sample. So what we have done here is estimate the area fraction of grain size, of large grain size in this sample. So what you see here is slices here between 0 and 2 millimeter. The fraction of large grains was about these values. And where we would measure the sample, then we would have a different fraction of large grain size. And what we have tried to do is correlate the fraction of large grain size measured by Lumet and the fraction of large grains by metallography. What you can see here is that you have actually a very good correlation between those two in the range of interest. So it tells us that the measurement of grain size using Lumet is an average of the grain size in the zone which is measured by the pulse. And it's also a very good tool to predict whether this particular temperature is susceptible to the presence of abnormal grain growth. Similarly, here, a very important case study which have benefited from these capacities, studies which has been done in Baosteel in China, in which they were designing a new alloy for a large ship where they would be aiming for very high capacities. And what they have done is the same type of studies where they would do isothermal holding in a niobium steel, and they would be able to identify what is the amount of niobium required to avoid the presence of abnormal grain growth in their temperature of treatment. So you can see that as they would increase the niobium content, the abnormal grain growth occurring at this temperature slowly is pushed towards later time to the moment where it just vanishes completely and it's avoided abnormal grain growth in this case. So that's an interesting case of studies in which Lumet was used for very applicable industrial studies. So following this type of grain size measurement during static isothermal holding, I want to show you what can be done in application for hot rolling. So of course, we all know that Gleeble is capable of applying deformation on sample in order to conduct studies on recrystallization following those deformation. This is a typical case for hot rolling processes. This treatment is consisting of sharp rise in temperature up to 2000 degrees, and then we lower the temperature to 900 degrees, apply a deformation of 20% or 40% strain, and then hold at 900 degrees for the recrystallization to occur. The picture that I show you here is the setup that we have used. There is a quenching nozzle here to quench the sample after the treatment, the thermocouple. This is the extensiometer to measure the strain during deformation. And left is behind a spot in which the laser will be fired. So what you can see here in this figure is the grain size varying with time during this recrystallization process. And the red curve corresponds to the strain of 20% and the blue curve 40% strain. What you can see is as we increase the strain, the onset of recrystallization occurs much earlier, corresponding to this sharp decrease in grain size, what's called grain refinement during recrystallization. And so here, Lumet was able to capture this recrystallization occurring after the deformation. You can access similar results in these studies, which have been done in 2008, where all the setup and techniques is described in detail. So now, of course, we were always interested to try measuring during the deformation. So I've taken like 3 slides to illustrate what can be done, but I've written it's an attempt on measuring property during deformation because still work needs to be done in order to publish those results and reassure ourselves that measurements are possible during the deformation. So the Lumet features a system which can move the laser simultaneously to the stroke of the Gleeble machine. That's an important feature so as to ensure that the measurement remains at the center of the sample in which the strain is captured. So here is a quick illustration of what's happening for a wave which propagates into a cylinder. You can see that it's a complex propagation mechanism which consists of constructive and destructive interference, and sometimes the waveform can be very tricky to analyze. What you can see here is if we simply do a cylinder specimen, we have a reverse in the polarity of the echo, which can sometimes cause a problem in the measurement of attenuation. So I just show you this to give you a hint of what we have done to try to improve this type of measurement. We've simply machined small facets on the sample to make sure that the wave would be generated and reflected on flat surfaces. The result of that is that this is a waveform which is much cleaner, easier to analyze, and so we could go further into this type of measurement. Here in this figure, we can see a typical stress strain curve where we have the increase in stress as the strain increases, up until a moment where we see a decrease in the flow stress corresponding to the moment where the recrystallization occurring dynamically this time starts to begin. And so what I have tried to do is take those waveforms, analyze the attenuation and plot it as a function of strain to see if there would be some correspondence between the moment where we see a decrease in flow stress and the attenuation signal. So what you can see here is that there is indeed a sharp decrease in the attenuation signal, which is for now very hard to interpret in terms of microstructure property, but at least it gives you an indication that this type of machine can actually give you an indication on the moment where the dynamic recrystallization occurs. Of course, I've done several situations in which the strain rate this time is changed. If in metallurgy, if we decrease the strain rate, the dynamic recrystallization will occur at lower strain. That's what we see in the stress flow through curve. The green line, which is a very low strain rate, the dynamic recrystallization starts at about 0.15 through strain. When it only occurs above 0.2 or maybe 0.3 strain in the case where the strain rate were 0.1 second minus 1. And here on the right hand side, you can see that indeed we see this decrease and this minima occurring slightly later in the case of the attenuation signal. So this gives us a promising result, but at this stage, I think I would just encourage everyone to continue this type of studies and try to work towards eliminating correctly this problem of diffraction. As the sample shape changes during the deformation, this becomes a little harder to interpret only the diffraction, the scattering contribution, and separate the diffraction contribution from the waveform. Okay, so remaining with stills, I'd like now to talk about the speed of sound, the velocity, how this looks like. As we raise the temperature in still, the speed of sound decreases non-linearly because of the magnetic property that has this ferrite phase BCC. Up until a moment where there is a discontinuity here, which is the Curie temperature. What we see here is the moment where the fractions of austenite starts to raise. Here is 5% of austenite, and here by dilatometry we could see it's 95% of austenite. What I want to show in this slide is that this is not very obvious in a velocity plot to look at the austenite formation. And I illustrate the reason why here in this plot. If we look at the speed of sound for BCC ferrite in black and the speed of sound for austenite FCC, we see that in the range of temperature where the austenite formation occur, those two velocities are very similar. It is therefore often considered a challenge to measure the austenite formation using this parameter. However, if you look at the austenite decomposition, you can see in this range of temperature, 700 degrees, 750 degrees, that those two velocities are very different. And therefore, we will see that this is possible to measure the austenite decomposition. But before moving to the austenite decomposition, I wanted to try to show that there is other parameter, the attenuation, that can probably give us a sign of the austenite formation. As you can see that here, the blue signal here, the attenuation, varies very importantly during the austenite formation. I've shown you here a very old paper from 1972, which have shown this type of behavior in which the magnetic transition is often accompanied by a rise in the attenuation. And then, of course, as the austenite formation occurs, the austenite is non-magnetic, the attenuation decreases again. And then this rise of attenuation corresponds, of course, to the increase in the grain size of austenite. So moving on to the austenite decomposition this time, as I was saying, in red here, you've got the cooling curve here. And the cooling curve here shows a sharp transition that can be utilized the same way as we use dilatometry curve to measure the austenite fraction upon cooling. This type of method uses a simple lever rules where we have the velocity in austenite minus the velocity in the two-phase region divided by the ratio of velocity, the difference in velocity in the two-phase domain. So you have the velocity here in austenite, velocity in ferrite here, and by using this relationship, we have a very good correlation between dilatometry and Lumet measurement for the austenite decomposition. I want to show you here a different type of cooling condition to show you that because we have a high repetition rate for this sensor, even at very high cooling rate, 150 degrees per second, we have still a very good agreement between the velocity signal measured using Lumet and the dilation measured using the dilatometry. This can be applied to dual torch welding simulation as well here, where we have the austenite decomposition occurring during the first cooling and the second cooling here as well. Very good agreement during this test. So velocity, as I said, was used here to measure phase transformation, but it can also be used to measure recrystallization. This is the purpose of these slides, where we have here a dual phase steel, which is cold rolled. You can see here the microstructure of the as cold rolled sample, which is consisting of ferrite, perlite, and benite. And this is elongated in the direction of rolling. After the recrystallization, we end up with a ferrite plus benite microstructure in which the grains are equiaxed. And this recrystallization has occurred during an isothermal holding at various conditions. what we are going to do is evaluate the change in velocity during this isothermal holding. And so I show you here the velocity here as a respect of time during this isothermal holding. What you can see is that it does change in a non-expected fashion, I would say. I guess this is because we have a change in texture in the sample during recrystallization, and this change in texture involves a change in the distribution recrystallization, or in the distribution of orientation of grains. And you can see here that we have corresponding microstructure here, stage A, where the recrystallization has barely started, B, where the recrystallization is partly going on, and C, where the recrystallization is almost completed. We've done this in those three temperatures, and by using this processing those velocity signal, we were able to acquire the recrystallization kinetics for those three conditions in 3 tests, when by microstructure analysis it requires many interrupted tests to acquire this recrystallization fraction. So here it's a very important point with this machine where we have a really large gain in time for acquiring this type of measurement. I'd like to show you this same type of study, but for an industrial case in which in galvanizing line, this type of study is very important. We need to have a reheating of a sample, which is initially cold rolled, so as to recrystallize the sample. This recrystallization will occur in the two-phase domain, so we have to be sure that the austenite formation and the recrystallization do not interact with each other, because it would lead to heterogeneous microstructure which are non-desirable. These are the initial microstructure of this dual phase steel with the composition. Again, this is a microstructure composed of ferrite, bainite, and perlite. And what we can see here is this variation of velocity during the recrystallization. Same as before, we have a sharp change in velocity during the recrystallization. To convince ourselves that this change in velocity is actually due to the recrystallization occurring in the sample, we've reheated the sample a second time from the recrystallized state, and we can see that the velocity did not vary at all during this change. It is possible to go much further into analyzing this signal by doing texture analysis, and what you can see here is an intensification of this gamma fiber typically seen in this type of alloy. And this type of measurement can be combined with velocity signal to illustrate quantitatively what change in velocity should be expected in this type of cases. Of course, in industrial case, we are not interested only on isothermal holding, but we are interested in recrystallization occurring upon continuous heating. So that's what I'm showing you here. This is a little bit trickier because the recrystallization here will be seen as a change in velocity, like you can see here. And it's not always very easy to decompose whether or not this recrystallization occurs during or after the onset of austenite formation. So what we have done here is conducting dilatometry study and microstructure study to have an idea whether this type of signal could be used to infer whether the recrystallization occurs during the austenite formation, which is the case here. We see no sharp increase related to recrystallization up to the austenite formation. When we see here at a lower rate of heating, this sharp increase due to recrystallization. So we could use this machine to determine that the recrystallization has occurred before the formation of austenite. This is here this illustration at different heating rate. You see at low heating rate, recrystallization occurs fully, when at high heating rate, the recrystallization occurs much later and overlap with the austenite formation. Attenuation signal shows also strong changes in the values of attenuation during recrystallization. Of course, this is due to the change in texture, which affects the attenuation as well. So this is what we see here to summarize these slides, that during real industrial heat treatment, Lumet can be used to determine the occurrence of recrystallization, but needs to be completed by dilatometry study so as to get information on the austenite formation, which cannot be measured very easily with this system. So again, Lumet here is a very complementary tool to the already existing sensor in the Gleeble machine. Okay, so moving on to another classes of alloy. Here I have a few slides on superalloys. We will be seeing first nickel-based superalloys and then cobalt-based superalloys. These two types of alloys are highly anisotropic in their elastic properties and are also very good candidates for studies using Lumet. This type of alloy here is Inconel and is used in part of aircraft engine. And those alloys here contain small precipitate. They are called delta precipitate here, which will dissolve during the homogenization treatment of those alloys. And the dissolution of this precipitate need to be controlled very accurately because they will affect the grain growth of those phase, of this matrix phase. And if the dissolution occur heterogeneously, then we will have again the presence of abnormal grain growth. What we have done is an isothermal holding at 1050 degrees, typical temperature for homogenizing these alloys, and quench at different time the sample. So I'm going to show you here at the time of 75 seconds, which is early on the beginning of holding. We see here that there is patches of grains which have grown substantially, while patches of grain have remained very small. And this is a typical sign that in those regions of small grains, the dissolution of precipitate has not yet occurred, pinning the grain boundaries and avoiding the growth of those grains. So this typical microstructure should not be kept at low temperature, as it would damage, as it would lead to quite heterogeneous microstructure during forging. It is necessary to wait until the dissolution occurs fully and when we have recovered an homogeneous grain size distribution, as you can see here at 900 degrees. And the goal of Lumet studies was to see, can we use Lumet to know what time should we hold the specimen to reach an homogeneous grain size. So before, of course, we've done some validation with microstructure. We looked at the grain size, equivalent area diameter. We looked at the grain size maximal in the microstructure using metallography. We looked at the distribution of grain size. And as I said before, here in these two curves here, which corresponds to the square and triangles, they are like early on the treatment, you can see a much wider distribution. Here it's Dmax over A quad, much wider distribution at early on in the holding than afterwards. We've built a calibration as was done with austenite in steel. We've done it the same. Calibration between the grain size measured by metallography and the B parameter measured using Lumet. And then we've measured the grain size. And you can see here we have this grain size measured using Lumet with respect to the time. And here the dots are measured by metallography. You can see first good correlation between metallography and Lumet studies. Second of all, you can see a very good repeatability between the measurement using Lumet. So here it's not like in the example I showed you before. The bulk of the sample is large enough that we have a very good repeatability in the grain size, although the occurrence of abnormal grain growth is present. And so we try to go a little further in analyzing the different stages of grain growth. You can see there is stages of very low growth rate, where the grains are pinned by the precipitate. a stage of rapid grain growth, where the precipitate dissolve heterogeneously in the microstructure, and then we come back to a stage of normal grain growth, in which the precipitate are fully dissolved in the structure. So by doing this small modeling, we can actually determine the fraction of large grains and suggest to the industrial what is the time required for fully dissolving this precipitate in this alloy by one single test. So we have to remind ourselves here, this type of studies require a little bit of preparation, constructing a calibration, validating these measurements. But when this work is done, Lumet can be used as a single test to advise in a specific condition the industry in terms of what time is required for fully dissolving the precipitate and recovering an homogeneous grain size distribution in the sample. So remaining with superalloys, we have now cobalt-based superalloy, where we have done analog type of study. Those alloys are very important in the field, in the medical field, where they are used for implant. And so again, here it's very important to control the grain structure in those alloys, because they control the ductility and strength of those alloys. You can see here the microstructure is composed of equiax grains, which contains twins, which are annealing twin, and those twins are typical for those alloys. And maybe I just want to make one note on those twins. These are considered as grains. That is to say that we have to decide when we build a calibration whether we measure the grain size including twins or excluding twins. And so, of course, this is to the choice of the developer of the calibration, but we've chosen to consider twins as normal grains, as they have a discontinuity in the crystallographic orientation, the same as between typical grain boundaries. Typical twins are considered as high-angle grain boundaries, so they should be considered as normal grains. We've developed this calibration here, equivalent area diameter, including the twins. And so we have developed this calibration using these B parameters, same as we have seen in austenite and nickel-based superalloy. You see here there is a good correlation between these tests. And in addition to the case of nickel-based superalloy, what we have done here is completed this calibration with a temperature contribution, so as to be able to account for changes in temperature during the heat treatment. You see here it's this contribution in temperature varies slightly non-linearly in the temperature range that we have measured. And so by simply using this relationship, we are now able to extract the grain size in a sample during a heat treatment. So here are an illustration of the result that we have obtained. So we have three different holding temperature, 1200 degree, 1150 and 1100 degree. And we have here a large grain size, rapid grain growth, at high temperature, whereas very small grain growth occur at 1100 degrees. These are two different alloys. One is called L605 and the other one is called CCM. And those two alloys shows very different growth rate in those same condition. I'm sorry. So here again, you can see that this Lumet was capable of capturing growth rate in different alloys for these cobalt families. So to go further on those studies, we use this calibration that we are now reassured is operating fine, and we looked at the same type of studies I've showed you earlier on static recrystallization, in which we do an initial deformation at a strain of 20% at a temperature ranging from 1000 to 1100 degrees. And then we will look at the recrystallization of this structure during the subsequent holding. The setup is shown here, and we have here an illustration of the stress strain curve measured using the Gleeble machine. You can see here in these three conditions, we have a raise in the flow stress, showing no sign of reduced inflow stress. That is to say, we have no occurrence of recrystallization occurring during the deformation. So all the recrystallization will occur after the deformation. So here is the result where we have the grain size in the vertical axis, time in the horizontal axis. You see here the grain size is always the same, not very much affected by the temperature during the strain. And as the time is passing during the isothermal holding, we have a grain refining occurring during the isothermal holding. And this grain refinement occur at different time depending on the temperature at which the deformation was applied. So you see that in the three conditions, we were able to capture the grain refinement occurring during the deformation. So to finish, I have 3 slides on an alloy which becomes more and more interesting because it's a light alloy. It's titanium. So the very first study that we have done using this alloy it's not an alloy, actually it's pure titanium, where we wanted to see if can we capture the transformation between the HCP to BCC phase. So in this pure titanium, HCP is the phase stable at low temperature, and BCC beta is the phase stable at high temperature. And what you can see in this example is that in the same as in steel, we can capture the change in velocity quite well. As we heat the sample and cool down the sample, we can see the hysteresis corresponding to the beta formation and beta decomposition in this metal. But more interesting in titanium is titanium alloys, which are widely used in industry. And so in this alloy, which is alloy 5553, the phase is beta at room temperature, and the hardening of this alloy is obtained by the formation of this alpha needle phase, which starts to grow at the grain boundaries of the beta phase. So as we hold the sample at high temperature, the beta phase will decompose, and the formation of alpha phase will start to occur at grain boundaries. The longer we wait, the more the fraction of this alpha phase will be in the sample. And as the velocity in this alpha phase is different than the velocity in the beta phase, we can actually measure the fraction of alpha growing in the sample during the time using the velocity obtained by the Lumet measurement. And of course, as we have done in all the studies, we've validated our measurement using metallography. That is to say, by analyzing the phase fraction in this sample. Those studies are not always very easy because it involves thresholding the color of gray. So it's always a little bit difficult for individuals to find the right threshold and obtain consistent measurement on the phase fraction. Whereas using Lumet, we let the sensor capture the change in the velocity, and we simply then have to normalize the velocity change so as to obtain the phase fraction. So in conclusion here, I think I want to point out first that this sensor is built by competent people joined by the team at Gleeble and Technar, and we support the user in terms of their machine, their analysis throughout their use since about now 10 years. And I think people that are using machine like Lumet should not be afraid that they will be supported during their use, and they will be provided expert advice by a great team of people. The second thing I want to see is that I have shown you that a wide range of metal can be used and a wide range of metal can be applied to this type of sensor, and a wide range of metallurgical property can be applied. Although we have to validate in a first stage measurement with microstructure so as to reassure ourselves that the subsequent study, which will be done much faster, will be correct. So in conclusion, I will be just finishing by saying that this sensor can indeed accelerate investigation in metallurgy and provide much reliable value for the metallurgist. So on this, I will thank you all for attending, and I will hope to answer some of your questions. And then I let you the mic right now.
Thanks, Thomas. Great job. Thank you for the presentation, but also for the past 10 years of work that you've put into this with, again, a lot of great people at UBC, up in Canada as well, and Technar, a lot of great work. So developing this, and even the software that I know you spent a lot of time working on. So thank you. We do have a handful of good questions. We're almost out of time, but I'm going to go a couple minutes long, if that's okay, because there are some good questions here. First question, I was talking about, you mentioned round samples, and that was an interesting tactic you used to kind of shave off a side of that to give us a flat space there. But we're wondering about the ability to test on torsion specimens. I know you have a torsion unit, had a torsion unit at UBC. Have you ever tested during torsion testing, or considered it, or on torsion specimens after testing?
Yeah, thanks. That's a great question. So we unfortunately could never do this test because our machine Lumet was attached to the Gleeble 3500 and not to the torsion machine. And but there is no limitation on the capacity on doing this. The problem will more probably be on analyzing the result, as during torsion, the properties in the sample are not homogeneous through the sample. So as the wave will propagate through the diameter, it would be seeing different amount of strain through the sample. So I guess additional work will have to be done on measuring the microstructure during through the thickness of the sample, to correlate the ultrasound measured in this torsion sample and the torsion stress measure in the test.
Okay, thank you. The question here says, laser shots generate both longitudinal and shear waves. Can the Lumet sensor pick up shear wave signals or particle vibration parallel to the surface?
Yeah, that's again a great question. So in the conventional configuration of the Lumet, it is being set up to generate mostly longitudinal wave. It can be changed simply by increasing the size of the generation spot slightly to enhance the formation of shear wave initially. But shear wave will always be generated inside the sample as this longitudinal pulse propagate through the sample, but by what we call mode conversion. So shear wave will always be present. And detecting those waves is often a challenge, as they have a small contribution perpendicular to the surface of the sample. And so Lumet is not extremely sensitive to those waves, but there is ways we can change slightly the optical setup so as to improve the capacity of detecting those shear waves.
Okay, thank you. A question here says, how do you compare the sensitivity of the laser ultrasonic with conventional piezo-based method?
Okay, well, I would say piezoacoustic sensors are different in essence because they are generating a pulse of a narrow frequency bandwidth. And so Lumet, by generating those waves using a laser, can generate a pulse with a much broader range of frequency. So unless you have an array of piezoacoustic sensors, Lumet will always be more interesting for metallurgical studies, thanks to the fact that we have access to the frequency dependence of ultrasound pulses.
Great. And you may have discussed this a little bit, but what is the maximum thickness of nickel-based alloy for which you can obtain back wall echoes? So I guess we're looking also, minimum thickness or maximum and minimum thicknesses. You can talk a little bit about that.
Yeah, for sure. So in terms of the minimum thickness, I would say below 1 millimeter, it starts to be difficult to extract the longitudinal pulse. As the sample becomes thinner and thinner, the whole sample starts to vibrate. It's like a plate wave, and so we don't see any longer the longitudinal pulse unless we apply very, very strong filtering of the low frequencies. In terms of the highest thickness that can be done, it depends on the attenuation of the material. We've been conducting tests in UBC with thicknesses up until maybe 15 millimeter, but if the sample attenuates a little less, we could probably go up until 20 millimeter or something like that. So it's roughly between 1 to 20 millimeter, I would say.
Okay, great. Can the elastic modulus of metal crystal be measured directly using a Lumet?
In terms of elastic modulus, what we obtain is the compressibility modulus, which can be often reduced as the Young modulus if we want. And we can rarely, well, this is simply by if you measure the longitudinal velocity, you will obtain the longitudinal elastic modulus or compressibility modulus. If we are able to measure the shear wave velocity, which is possible, you will have access to the shear modulus.
Okay. Let's see, a few more questions here. How sensitive is the Lumet signal to the surface roughness of the sample or thin surface oxidation?
Yeah, that's a great question. So it is recommended before a test to have a sample which has no oxide scale from the hot rolling, because this tends to reduce the reflectivity of the light and therefore reduce the amplitude of the signal that we measure. So it's often a good idea to polish the sample or to have a sample machined which has no oxide scale from the hot rolling. After, the little oxide which forms during a Gleeble test is not a problem, as this oxide will be removed each time that the laser fires on it. So I would say oxide scale, it needs to be removed. Oxide during Gleeble test is not a problem.
Okay, and then also I know when the laser is striking at the specimen, after a while it will burn a little hole in the specimen. So I guess, and that may be dependent on the frequency that you're shooting it. How long can you run a test for, or
right?
You talk a little bit about what happens to that specimen, because it does get affected.
Yeah. So indeed, the laser that we use for generating those waves has enough power to ablat a little bit of the sample to detach some atom from the sample surface. And if about 600 to 1000 pulses are generated at the same location, it tends to damage the sample surface. So whenever we reach this stage, we can simply move the laser spot a little further on the right or left of this initial spot and move further into the test. So in UBC, we've done tests which reach up until 3 hours, 4 hours. There is not really any limitation in time, as long as you can have a zone on your sample which is homogeneous in temperature, and then you can then move the spot when you reach a certain amount of damage.
Great. So we're about 6 minutes over. I wanted to maybe ask a couple more questions, and questions are kind of coming in pretty fast right now. So what I would ask, I think we talked before this call that you'd be willing to maybe follow up with some questions after the call, either through email or potentially set up a quick call with some people if they're interested. So thank you for that. So I have a couple of questions here. Can this sensor determine constitutional equation? If so, can it measure volume percent growth over time?
Constitutional equation. Sorry, can you repeat the question?
Yep. Can this sensor determine constitutional equation? If so, can it measure volume percent growth over time?
Oh, equation?
Yeah.
Yeah, no, so, I mean, at least in my experience, I've only been working in the solid state. I've never really gone further into looking at the onset of liquefaction. And so I don't have much experience and expertise in saying what could happen in this case. So I would rather not go move further.
Okay. I think actually a lot of the questions here are just people thanking you for your presentation and telling you did a great job. So I'll echo their sentiments as well. This is great. So I do want to be respectful of everyone's time. Just in closing, again, obviously, Thomas, thank you for this great presentation. I've heard similar presentations in the past, but I always do learn something new. So great job. If anybody does have questions for Dr. Garcin, please feel free to reach out to him directly or reach out to me or anybody on the DSI team. We're happy to make that introduction. I also want to thank the folks up at Technar, who've been great partners with us on the Lumet project. So thank you to that whole team. A lot of really smart people up there that have helped us develop this product. If anybody has any technical questions about the Gleeble, I've mentioned this on every webinar. Please feel free to contact our service team. The best way to do that is to go and sign up for the service portal. So if you are a customer, go to that service portal. You can do that at gleeble.com. And you sign up for the customer support portal. There's user-based, there's a knowledge base, and you can also create support tickets. That's a great way to get support. If you have any questions about how Gleeble can support your research, please do reach out to anyone on the DSI team. We're happy to help. Again, thanks everyone for joining us. We appreciate your time, and please do remain safe and healthy. Have a great day.